One of the great things about calculus is that it lets us quantify things that are weird, things that change. One such problem is called the area problem. The idea is to take the area underneath a curve. When the function is linear, things are simple. The area that is created are simple shapes that we already have formulas for, like triangles and rectangles. The problem presents itself when we want to find the area under something like a quadratic formula. We have to be quiet. The species we're looking for, really rare. It's also really easily spooked. Do you hear that? Oh, come on! Oh, wow! Oh my god! This is one of the best specimens I've ever found in all my years in the field.
What is that, a wave?
A wave? What do you think we are, physicists? This is an integral. The integral can be defined as the area under the curve, and calculating it presents some problems. The area under a curve is important to math and physics because many quantities have the same value as the area under the curve. Take, for example, acceleration, or the change in speed over time. You can obtain the velocity, or the change in distance per unit time, by taking the area under the acceleration curve. Now, this doesn't mean that the velocity is physically the area under the curve. Area and velocity are two very different quantities. To see how we go about calculating the integral, let's head to the kitchen. What we're going to be doing today is finding the area under this curve using calculus. We lose some accuracy, but we can represent the entire graph as a couple of rectangles. And the sum of those rectangles gives us the area under the curve. You're losing pieces of the area when you cut the rectangles. You're right, but if we do this, the rectangle approximation gets more accurate as we use more rectangles. This rectangle approximation is actually called the Riemann sum. I will now cut this area into an infinite number of rectangles. Professor Daisy is out of order at the moment. She is stuck counting to infinity, which means that she will never reach the end and will never be able to give us what the exact area under the curve is. Luckily, we have calculus. The equation of the definite integral looks like this. In the integral notation, a and b are the x-axis limits of your graph. It's okay if the formula still looks confusing, but explaining it is for another video.